Hey everyone, welcome back to The Explainer. Today we're hitting Distributed Data 35, and honestly, I am super pumped about this one. We are demystifying one of the most notoriously difficult, yet absolutely essential topics in all of backend system design, consensus algorithms. If you've ever wondered how the massive distributed architectures at places like Google or Amazon keep from just totally falling apart, well, this is the secret sauce.
Here's our game plan for today. We'll kick things off by defining distributed consensus. Then we'll look at the nightmare that is system failures. After that, we'll dive into majority voting and quorums, break down replicated logs and their flow, and finally, wrap up with the real-world costs of using consensus.
All right, Section 1, defining distributed consensus. A single truth.
So think about this for a second. How do independent machines, literally sitting in different server racks, maybe even on totally different continents, actually agree on a single, indisputable truth? I mean, there's no grand master computer pulling all the strings here. So coordinating them, yeah, it's a massive, massive puzzle.
Basically, consensus is about getting multiple nodes to agree on the same value or decision. But here's the kicker. That decision has to be completely irrevocable. It's not just about agreeing in the moment. If a node makes a proposal and then literally catches fire a second later, the rest of the system absolutely must remember and uphold that exact same decision. No takebacks.
Now, why should you care? Well, imagine you're building a system for booking flights. Two users click buy on that very last window seat at the exact same millisecond. Your database nodes have to reach a consensus on who actually gets the seat. If they don't, you're looking at double booking, corrupted data, and, some seriously angry passengers. You also need this kind of rock-solid agreement for electing a single database leader, setting up distributed locks, ensuring atomic commits across partitions, or safely rolling out configuration changes. It's absolutely crucial.
Moving on to Section 2, the challenge of failures. Unreliable systems.
Okay, so if consensus is the holy grail, why is it notoriously so hard to pull off? Well, let's face the harsh reality of distributed systems. Partial failures are they're the norm. Machines die without warning, network links snap. But honestly, the really sneaky issues are unbounded delays and process pauses. Like, say a node pauses for a 10-second garbage collection cycle. It's completely frozen. When it finally wakes up, it has no clue it was essentially asleep, and it might just start blasting out wildly outdated information. Total chaos. And that brings us to the absolute nightmare of distributed systems, the dreaded split-brain scenario. Picture this. A network partition randomly slices your database cluster right down the middle. Both halves lose contact, so nodes on both sides panic and promote themselves to be the leader. Bam! Now you've got two leaders, both independently accepting conflicting rights from your users. And the worst part? When the network finally heals, it is mathematically impossible to cleanly merge that data. You've officially suffered permanent data loss.
Earlier attempts tried to handle coordination with something called a two-phase commit, basically relying on one single coordinator node. But take a look at what happens here. If that one coordinator crashes right after telling everyone to get ready, the participant databases are just left hanging. They're indefinitely stuck in doubt. They don't know whether to commit or abort, completely locking up the entire system. Obviously, we need a setup that doesn't rely on a single point of failure.
Which brings us to Section 3, majority voting and quorums, surviving failures.
To survive these random node deaths, consensus algorithms use what we call quorums. A quorum is just a strict majority. So say you have a cluster of 5 nodes. You don't actually need all 5 to agree. You just need 3 out of the 5. If 2 of your nodes are completely offline or broken, no big deal. Your database keeps right on processing rights because those 3 remaining nodes form a perfectly valid quorum.
And here is the absolute mathematical beauty of it all. The ultimate safety guarantee is that there can only ever be one majority in the system at any given time. Think about it. If you need 3 out of 5 votes to elect a leader, you literally cannot elect 2 conflicting leaders at the same time. You can't slice 5 nodes into 2 groups of 3. The math just flat out prevents the split-brain bug. It's brilliant.
Let's dig into how we actually build this. Section 4, replicated logs and flow. Practical consensus. At the end of the day, it's really all about state-machine replication. Just think of the replication log as a single timeline of truth. If your leader node appends a sequence of write commands to its log, and the follower nodes replicate that exact same sequence in that exact same order, well, every single node will independently calculate the exact same final database state.
Let's walk through the actual sequence of steps here, looking at algorithms like Raft or Paxos. Step 1. You elect a leader and give it a unique epoch number. Now, this epoch number is literally a lifesaver. It's a built-in safety net that instantly overrules any old zombie leaders. If an old leader wakes up from a long pause and tries to issue commands stamped with, say, Epoch 4, but the rest of the cluster has already moved on to Epoch 5, the nodes just reject the zombie, period. After that, the active leader proposes new data, and it only officially commits that data once a strict majority confirms they've safely stored it. So, notice what's happening here. We actually have two separate voting phases. You need a quorum to elect the leader, and you need a quorum to accept the data. Because both phases require a majority, those two majorities absolutely have to overlap by at least one node. And that overlap, that guarantees that any newly elected leader has mathematically definitely seen the latest committed data from the previous leader. Nothing gets left behind.
All right, last part, Section 5, the costs of consensus. Trade-offs in reality.
So we've built this incredibly safe, mathematically bulletproof system, right? But let me ask you this. If it's so robust and completely protects us from data loss, why on earth don't we just bake consensus into every single read and write operation we do? Well, because nothing in engineering is free. Consensus requires a synchronous conversation over the network. The leader has to propose the data, wait for the packets to hit a majority of followers, and then wait for them to acknowledge it. That creates a massive latency bottleneck. Plus, if a network partition isolates more than half of your nodes, your system loses its quorum. And to maintain that ironclad safety, the system will choose to completely halt your writes. You literally sacrifice all availability.
In the real world, out in production, consensus is incredibly sensitive. A flaky network can easily trick your nodes into thinking the leader died. That triggers a continuous, frantic loop of leader elections where literally no actual work gets done. And because this logic is so ridiculously complex, backend engineers pretty much never write consensus algorithms from scratch. Instead, we offload all that heavy lifting to dedicated, battle-tested tools, things like Apache Zookeeper or etcd.
To wrap up the philosophy here, consider this thought. A large-scale outage can stop the system, but it cannot corrupt the consensus system by causing it to make invalid decisions. That is the core takeaway. Consensus prioritizes absolute data safety over absolutely everything else. It will willingly crash your application and refuse service rather than even risk permanently corrupting your data. So I want to leave you with this to chew on today. Take a hard look at the systems you're building or studying right now. Are they genuinely coordinated using consensus, or are you just sort of relying on luck, crossing your fingers, and hoping for the best when the network inevitably breaks? Thanks for hanging out with me for this explainer. I hope it really changes how you look at distributed systems. Catch you next time.